Hi, and welcome to Spiro School of Math. Today, I'm going to be teaching a lesson about decaying exponential functions. This video is just a refresher for some students that may have missed the class, and it's just to get them up to date about the lesson 5.5 of decaying exponential functions. The question that we'll be looking at today is question 1 on the practice questions of 5.5, page 289. The question says, a 100 milligram sample of thorium-233 is placed into a nuclear reactor. After 10 minutes, the sample has decayed to 73 milligrams. Use the following equation, which it gives, to answer the following questions. So the key parts of this question are 1, that the fact that our original sample is 100 milligrams. 2, that after 10 minutes the sample becomes 73 milligrams, and 3, the equation that it gives us. Using these 3 things, we'll be able to solve the questions below.
Okay, so before we begin this question, I'm going to start off by kind of explaining, what the formula is and just the components of the formula and how we're going to use it to our advantage in the future questions. So here I'm going to enter in the formula that we're given in the question, which is n times t, which equals the original value of n times e to the power of the negative of the disintegration constant, which I'll just put as x for now, which is multiplied by t. So this is the formula that we're given in our original question. And it seems complicated when you don't know the components, so I'm just going to kind of break it down for you. So in order to do this, I feel like the best way is to visualize it. So to visualize it, I'm going to enter in a few numbers here that we will solve for later that in the original question. So for example, the original value of our sample is 100 milligrams. This was given to us in the original question, but the disintegration constant is something that we're going to solve for in the first part of our question A, but I'll just enter it in here just so that we can kind of visualize the formula. So 0.03 is the disintegration constant, and this is what we're given here. So obviously 100 milligrams, that is the y-intercept, and this is important because this is kind of the starting point of our exponential function, which seems kind of weird because the function goes up here, but if you were to visualize this as a graph, this y-axis would be the value or the mass of our substance, right? So 100 milligrams is the starting point, and the x-axis here would be time. And because we can't have negative time going in this direction, anything past this part of the y-axis does not really count for our question because we can't have negative time, right? And just to show that this graph is accurate, it says in the question that after 10 minutes the sample is decayed to 73 milligrams. So we're going to go here to 10 minutes, and we see that it's about 73 milligrams. And the reason that it's not completely 73 milligrams is because we rounded with the disintegration constant here, but if we did it more accurately, we would get a more accurate result. So how does this graph work? Well, because there is a function up here, and it is because these numbers down here are to the power of a function, we get an exponential function. So I'll give you another kind of basic example. So let's say I do y equals let's say 200 to the power of 2x, right? So obviously it looks kind of just like one line going up here, or one line going across here, and one line going up. But if we were to zoom in, we see that really it is actually a really fast growing exponential function, right? So it grows up really fast here and just continues to go up, right? And the reason that our function, the original function that we're given, doesn't do this is because the power here, the exponent, is so low. So for example, if we then change this to 0.0002, we would get something that doesn't go up for a while and takes a long time to go up. And then also our graph is going the opposite direction of this graph here because our number is negative. So if I change this to negative 0.02x, we would see that it is going the same way. And this makes sense that our graph is going this way because it is decaying and not growing. So this is just kind of a general understanding of the function, and I think it'll help you understand the questions that we're going to get into better.
Alright, so for question A, it asks us to determine the disintegration constant for the sample we are given. So I'm going to use some of the information given to us in the original kind of question. So the first thing we're going to use or write down is the equation we're given, which is mt equals original value of n times e to the power of the negative of the disintegration constant times t, which is time. Next, I'm just going to write down a couple key points. First being that the sample originally was 100 milligrams. It ended off at 73 milligrams. And this took 10 minutes. Alright, so now what we're going to do is plug these values back into the equation. So the 100 milligrams is the original value, 73 milligrams is the final value, and 10 minutes is the time. So 73 milligrams is the final value, 100 milligrams is the original value, times e to the power of the negative of the disintegration constant times 10 minutes. So now what we're going to do here is we're going to kind of like rearrange and solve for the disintegration constant. So first what we're going to do is divide by 100, so divide by 100 on this side. So what you do to one side of the equation, you have to do to the other side. So we're going to divide by 100 on the other side as well. And that gives us 0.73 equals e to the power of the negative of the disintegration constant times 10. Now what we want to do is we want to solve for the disintegration constant. So we have to kind of get the powers alone. And the way that we do this is we ln both sides. And ln is the natural logarithm. So it's log with the base of e. And what e is it's a constant similar to pi, except e is approximately 2.71. So we're going to do is we're going to ln 0.73. And we're going to ln e. Now ln e is equivalent to 1, so we're going to write 1 later, or negative of the disintegration constant times 10. Now what we're going to do is, again, ln e equals 1, so we're going to write that as 1. So ln of 0.73 equals 1, power of the negative disintegration constant times 10. Now what we could do here is when you ln something, or when you log something, you could bring the whatever in the power down in front of it and multiply it to the ln. So what we're going to do is we're going to erase this step here, just showing you that ln equals 1, and we're going to bring this down in front of it. So it's going to be the negative of the disintegration constant times 10 times ln e. So now what we could do is we could divide over ln e, which is equivalent to 1 to this side. So we have ln 0.73 divided by 1, because ln e is equivalent to 1, which equals the negative disintegration constant times 10. I'm just going to bring this up here to give us more space. So now what we're left with is the ln of 0.73, which is equal to the negative disintegration constant times 10. So what I'm going to do here to get the disintegration constant alone is I'm going to divide by negative 10. And what you do to one side, you have to do to the other. So I'm going to divide here by negative 10 as well. And this leaves us with the disintegration constant equaling 0.03147. 0.03147. And what disintegration constant is it's just how fast the sample that we're given disintegrates at, which is 0.03147 milligrams per minute. So for question B, we are asked to determine the half-life of Th233, which is our sample that we're given. So the first thing I'm going to do is just, again, write down some important things. So first of all, half-life is half of what we originally had. So in our case, our substance was originally 100 milligrams, but we want half of that. So what we do is 100 divided by 2, which gives us 50. So 50 will be half of what we originally had and what our end goal will be. So it'll be 50 milligrams. Now what we're going to do is we're going to plug this back into the equation that we were given before, so which is NT, which equals the original value of N times e to the power of the negative disintegration coefficient, which we solved for in the last question, which is 0.03. I'm just rounding it to that to make it easier, but it was 0.0314. And then times t, and t is what we'll be solving for in this equation to see how long it takes to get to that halfway point. So again, I'm going to sub in the rest of the values. So our final value is 50 milligrams. Our original value is 100. Multiply that by e times negative to the power of negative 0.03 times t. Now again, the process work here is going to be very similar to what we did in the first question. So we're going to start off by dividing the 100 over. So we're going to divide by 100 on this side. And what you do to one side, you must do to the other. So divide by 100 on this side as well. And we're going to get 0.5 equals e to the power of negative 0.03 t. Now what we're going to do is we're going to isolate for these powers so that we can solve for t. So what we're going to do is ln both sides again. So we're going to do ln 0.5, which equals ln e to the power of negative 0.03 t. Now again, we're going to use that rule where because we're logging or lnning something that has a power to it, we can bring this power to the front and multiply it with that log or ln. So what we're going to do is have ln 0.5 equal negative 0.03 t, and that is times ln e, which again is just 1. So now to kind of isolate for this, we're going to divide by ln e on this side. Right, divide by ln e on this side to get rid of it from this side of the equation. Divide by ln e on this side, which again is just 1. And just we'll bring it up here to give more space. So again, since we're dividing by 1, we're going to be left with ln of 0.5, which is equal to negative 0.03 t. And what we're going to do to isolate for t, we're going to divide by negative 0.03 on this side, divide by negative 0.03 on this side, and what we're going to be left with is that t equals 23.1 minutes. And that means that it takes 23.1 minutes for our sample, which is TH233, to get to half its original value.